So we've just been talking about some of the models of reality and how you can be a naturalist or a supernaturalist and what that means. If you've decided you're a naturalist and you only look inside the space-time continuum, you're going to have limited options for explaining things. But whatever you've decided, it's really important to remember to be careful of drawing lines in the sand and saying, this is it, because no matter how much we see, for example, the blind man who had touched the elephant's side, he knew the elephant was like a wall. And he said, I know it's a wall. And he didn't want to listen. And so I think we have to keep on listening without fear. Our God is big enough. And I just want to say here, one of the other divisive ideas that turns up is the age of the earth. By the principle of parsimony, what seems to be true ought to be true. And there seems to be a contradiction between what the principle of parsimony says about Genesis. It says the first in the morning and the evening and so on. And what the principle of parsimony says about what we see in nature, that it looks old. And I think we need to just keep looking, hold an open hand, and wait on God. We know He said a day is like 1,000 years. We know the first 3 days, we got 3 days of making, 3 days of filling, and it may not have been a scientific explanation, but I'm going to hold it with an open hand because God could do it the way He wants to. He's not likely to make us look old or make the earth look old, but He could do that if He wanted. So rather than arguing and perhaps doing harm, let's hold it with a humble, open hand. For example, we had once been at the Badlands, and my daughter had picked up a dinosaur tooth. She had a tooth of an albertosaur, pretty little thing with jagged edges. And we had, after that, gone to a bike shop. And the people that worked there were from a very conservative background. And one of the children she was playing with had been taught that dinosaurs were hoaxes. And so when she said, look, I found a dinosaur tooth, he ran back to the house crying. We don't need to do that to our children and to those we send off to university. Let's remember that God is big enough. And whether He did it over millions of years or in 6 days, the point is we need to keep our eyes on Him and stay humble and wait on Him so that, like the blind man and the elephant, we can go back again and complete our model and see why the elephant could be like a snake in a wall and a tree, and still all of them would have kind of been right. They had a piece of it. Another part that often is difficult for people is the concept of homology. If I seem like an animal, that evolution is true and there's no God. That's often how it's interpreted, this idea of homology. Do similarities prove that God is not the creator? Is that the most parsimonious explanation? And this one I have thought about way more than the age of the earth. So I want to give you a little bit of what I've learned and suggest that probably this might be helpful as you make your own model and understanding of truth. So homology. Homo means same. Logi means study of. It's the concept of homology that predates the concept of evolution. It's older than the idea of evolution. Here you see vertebrate forelimbs. You have a hand, an arm, and you've got the humerus, the radius and ulna, the carpals, the metacarpals, and the phalanges. You say the same thing in a cat's leg, in a whale's leg, in a bat's leg. And by the way, it's the same pattern that's in your leg, the hind leg of a dog is in the foreleg of a dog. And so we call the bones by different names, but we have the same pattern of 1, 2, 7, 5, 5. You have the humerus, the femur, and the fibula and tibia, and so on. In the leg, you have the same pattern of 1, 2, 7, 5, 5. And in the leg, of course, the bones have different names. You have the femur, the tibia and fibula, the tarsals, the metatarsals, and phalanges. It's a pattern, a sameness that we turn up in different places. Let's look in history. How did this idea of sameness? It started by lumping like with like the cats are like each other. Here's a bunch of cats. The gulls are like each other. Here's a bunch of gulls. And the first person that started doing this was called Carl Linnaeus, the one who really systematized it. He was the father of taxonomy, or naming of the animals. This is from Berkeley, just so you can see that I'm not spinning this in any way. His system for naming, ranking, and classifying organisms is still in wide use today. Linnaeus' innovation was the grouping of genera into higher taxa based on similarities. But Linnaeus did not see this as any evidence of evolution. Instead, he saw or thought he was thinking God's thoughts after him. He was looking for the nature of God in creation. He wrote in the preface to a late edition of Systema Naturae, in Latin of course, but he said, "The earth's creation is the glory of God as seen from the works of nature by man alone." He believed the study of nature would reveal the divine order of creation. Again, this is from Berkeley. So you see that his faith in God encouraged him to observe carefully inside nature. He's one of the founders of biological science. Another man who's been very important, and there are others, so when I taught this in class I included other people, but I'm going to just focus on Linnaeus and on Owen and Darwin, and we'll see a little bit of what they're saying. Now, Richard Owen gave us many of the same terms used in anatomy and evolutionary biology, including homology. Owen famously defined homology as the same organ in different animals under every variety in form and function. So he was the one that came up with the term homology. Taking homology to its conclusion, again this is from Berkeley, Owen reasoned there must be a common structural plan for all the vertebrates as well as for each class of vertebrate. He called that plan the archetype. And here's something all the vertebrates have in common. However, Owen did not believe his archetype was anything like an ancestor. Rather, the archetype represented an idea in the divine mind which also foreknew all of its modifications. Owen was a supernaturalist, and he was thinking God's thoughts after him. And he said God had these great ideas for Katniss. He had another idea for grasshoppers, and he played with those ideas. They were archetypes in his mind. He was also the guy who came up with the word dinosaur. Here's a picture of him standing by a dinosaur skeleton, one of the first they dug up. So then Darwin came along, and he observed what we were just talking about a few minutes ago, descent with modification, selection for variation in the gene pool, like we do with breeding dogs. He saw that with Darwin's finches. And so from this information, he came up with the idea that over long periods of time, descent with modification, with natural selection or pressure from the environment could produce all the different kinds we see. He had no idea what DNA was or proteins were, or that the information was limited in the gene pools. So let's look at the two definitions of homology. Owen, who coined the term, saw homology as evidence of archetypes or ideas in the mind of God, expressed with many variations. He was a supernaturalist. And Darwin saw homology as evidence of common descent. So if you look like a monkey, you probably came from a monkey ancestor. You both came from the same ancestor. By this definition, homologous structures are inherited from the same common ancestor. This is a very attractive thing to naturalists who want to look only inside the space-time continuum. I'm going to mention him because of a booklet he wrote and because of his background. Gavin de Beer, an English zoologist and morphologist known for his contributions to embryology, anatomy, and evolution. He was a staunch evolutionist and a biographer of Darwin. He was also an honest man. And when he began to really look at what he saw, it didn't seem that homology defined by the way neo-Darwinists would really made sense for all the situations. Let's look at what he saw. This is Gavin de Beer. Now Darwin has given homology this new meaning. So now they've done a circular definition. If you have things in common that are homologous, they must have come from a common ancestor or they're not homologous. That's not the same way Owen described it. He said they're ideas in God's mind. But now it's been decided it is homologous organs that provide evidence of affinity between organisms that have undergone descent with modification from a common ancestor. And sometimes that's true. In other words, dogs are like wolves because they descended from wolves. But is it always true? Does it even make sense always? Let's look. So what empirical evidence, what would we expect to see if we looked into nature from Darwin's point of view? We would expect to see that homologous structures would be present in a shared common ancestor. In other words, you could draw a tree that makes sense. And the trees for different characteristics would match, because you can't have a different family tree for the same creatures. You can't end up with a family tree that explains the teeth and then different ones completely different that explains eyes. They have to match each other. Homologous structures would arise from the same embryological structures because they're going to develop in the womb. So if in a wolf the teeth develop from an infolding of the ectoderm in the embryo, it's going to be the same in a dog because they really did descend from a common ancestor. But are we going to see this with what seems to be similar characteristics from very different types of animals? And they would be built by the same developmental process and genetic information. We would expect to see that, but what do we see? This is a long time ago. In 1971, he said, Gavin De Beer published his short work entitled Homology, an Unsolved Problem. In his introduction, he said, it looked as if the concept of homology was at last soundly based and presented. No more problems in principle. However, it will be seen that it does. And notice he said, unfortunately does, because he had a model of reality that this didn't fit into super well. He points out that homologous structures may come from different parts of the embryo. And he gives several examples of this, but I'm just going to focus on limbs. In the newt, the arm or forelimb is formed from trunk segments 2, 3, 4, and 5. In the lizard, 7, 8, 9, and 10, 6, 7, 8, 9. In the man, from 13 to 18. And actually in birds, it's even farther. So it's played like a tune along the segments of the developing embryo spine. It doesn't come from the same bit, so it's a bit hard to see how you could have inherited it and then changed where it belonged in the body. There's another type of thing that happens in an embryo. In some types of embryo, as the original cell that was fertilized splits in cleavage, it sometimes does a little quarter turn. So it makes a spiral, and that's called spiral cleavage. And he's saying we can't figure out a pattern of how there could have been a tree for spiral cleavage. It says this spiral cleavage indicates an affinity between the different groups because it's difficult to see how it's such a very complicated mechanism. Remember, irreducible complexity. It's a complicated process with many different working proteins. Could have evolved separately by accident in each group. And the similarity or affinity is supported by other embryological and morphological considerations. In other words, they're using the same protein machines to do something similar, but you can't find an ancestor. Did the common ancestor develop by spiral cleavage? Or did many, many lose the ability? That you're finding them in tubularians, nemertines, marine annelids, and mollusks other than cephalopods. And I just put 2 examples up here of a marine annelid and a snail. But there's lots of other ones in those groups that don't use spiral cleavage. You can't draw a tree. No common ancestor for segmented animals. If you put your thumb on your back and run your thumb down your spine, it'll go dump, 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 dump. You can feel that our spine is in segments. Here you have segments along the spine of a dog, segments along an earthworm, segments along a grasshopper. And they would say, you might say, well, these animals are completely unlike each other. But when you look at the segments, you're actually using the same protein machines and some of the same genes to make the segments. And this is a paper that was published in around 2000. Another interesting case is the presumed homology based on overwhelming complexity of similarities, especially molecular or working protein machines between annelid, arthropod, and vertebrate segmentation. And this is 2003. Amongst other advanced features, the ancestral bilateral, and like the 2 sides the same here, was posited to be segmented. This implied the unparsimonious loss of segmentation in more than a dozen unsegmented phyla. In other words, they're having a really hard time drawing a tree that makes any sense with segmentation. Here you have another example where you'll have a working little protein machine doing a similar job to make very different structures. The protein in this case is from a gene called Notch, which is expressed as a protein. that's used in the development of the vulva in C. elegans, the sexual organs of C. elegans, the Drosophila or fruit fly eye, and the presomatic mesoderm or vertebrates, the part that goes on to become the muscles. And this is a paper called When is Homology Not Homology? It's much more recent. This problem hasn't gone away, and as they find out more and more about molecular biology, it's becoming more difficult. You get non-homologous genes giving rise to what seem to be homologous structures, and you have a pattern on the back of different wasps that seems very similar, but it comes from completely different mechanisms. This happens so much that they're now starting to talk about tinkering. And when they try to draw a tree, instead of the old-fashioned tree like this, they're drawing it with a circle. It's an unrooted tree, and you'll find this over and over in textbooks. So was there an ancestor? How did all this stuff end up? You can make a pattern. You can draw a tree like you would put like with like in the instruments of the orchestra. I don't know if you all did that in school. We had to do an exercise where you put the stringed instruments in a group, and you put the brass instruments in a group, and so on. And there are real similarities between them. But when you look at it, why are there similarities? Because of how their makers did it. If you look at vehicles, you can certainly lump like with like. You can put trucks and 18-wheelers, and you can put sedans and sports cars. And there are real similarities. You can put them together in categories, but does that similarity mean there was a common ancestor or shared ideas in the making? Because of these difficulties, they've come up with new words. And remember, we had the problem of falsification, that you can always make many different explanations for things, but the simplest explanation is usually the right one, Occam's razor. Well, here it looks to me like they're making complicated explanations. And homeoplasy is a word that says in biology and phylogenetics, it is when a trait has been gained or lost independently in separate lineages over the course of evolution. This is different from homology, which is the similarity of traits that can be parsimoniously explained by common ancestor. In other words, they had to come up with a different word for similarities that they couldn't explain, that seemed very similar. Then they came up with another word, bricolage, which means tinkering, accidental tinkering. This is a paper from 1998. It was right around in there that they really started struggling with it, and they haven't come any closer to a conclusion. The past 10 years of developmental genetics have revealed that most of our genes are shared by other species throughout the animal kingdom. Consequently, animal diversity might largely rely on differential use of the same components. In other words, you're not making new things by accidentally breaking protein machines by mutation. You're actually using a working machine in many different contexts. And so they're having to say, well, accidentally creatures changed genes around and traded off, and it worked perfectly. We made a new type of creature. Here are more of these complicated explanations. The anthropic principle. If you believe absolutely that there's nothing outside, if your presupposition is that there's nothing outside the space-time continuum, and you see that here we are standing, therefore you have to say, even though it was unlikely that it happened by chance, it did happen by chance because we, people, or anthropos, are standing here. And that's called the weak anthropic principle. There's also a strong anthropic principle. It's a circular explanation that seems to me quite complex and unparsimonious. And another that they come up with is parallel universes. You can see, if you study life, if you study the universe, that it's very unlikely that we're here at all. Not only all the complications of supposed evolution happening for life, but that the Earth would be at the right distance from the sun, that all the constants in physics would allow life. To have all of these things move together to make life possible is horribly unlikely. If you know much about statistics, you know that when you have the likelihood that something has happened, you're going to multiply the chances with each other, and you'll find out how likely it is to happen. And it's horribly unlikely. So they made the idea that maybe there's parallel universes, and since there are so many millions of universes, it happened in this one by accident. These are, to me, it seems so much more complicated than saying a designer was at work. Somebody guided this. Somebody's hands are involved. In Him we live and move and have our being.